Okay, so let's start for today. Today we'll continue with the coding theory. We'll finish talking about the entropy and we'll start the introduction into the next topic of advanced statistical methods. Now, you remember from last time that we were dealing with coding of random variables. So suppose we have a random variable which has some number of possible results, and these results come up with some probabilities, and depending on what are the probabilities of this, we want to encode them using strings from some alphabet to be as efficient as possible. Okay, so we basically take the values, assign them zeros and ones, and you want to do this in a smart way. Now, we have seen that when we want to compute, well, in some way assess what is more smart than, well, what's the smartest in terms of compression length, we can compute the expected code length as just the sum of the length of the code words multiplied by their probabilities, and we have found out using the results of concerning differential entropy and Kraft inequality that among the codes which are instantaneous, meaning that no code word forms the beginning of another, the expected code length is always larger than or equal to the entropy of the random variable. It is exactly equal to if the probabilities are equal to the base of the alphabet to the power of minus lengths of the code word. So if there exists a one-to-one relation between the lengths of the code words and probabilities, we have seen on several exercises where the equality holds and where the equality actually does not hold because of the code lengths needing to be integers. Now, we have also seen that if we proceed in a smart way, the expected code length will always be between the entropy and entropy plus 1. If we are talking about binary coding, this means, and a binary entropy, this means that the expected code length will be always between the entropy and entropy plus 1 bit. Now, assuming we pick a reasonable code, now it can be proven that an optimal code always exists. It doesn't have to be unique. Sometimes there can be different codes or possible encodings with both of them having the exactly same expected code lengths, and that such a code can be constructed using the so-called Huffman algorithm or Huffman code. The Huffman code works in such a way that at the end, short code words are assigned to more probable values and longer code words are assigned to less probable values. And it works on the base of concatenation and going through all of the possible values in one way, finding those which are the least probable, putting them together, building, well, basically trimming a tree into one of possible options into just one leaf, and then going backwards and assigning ones and zeros to the code as emulating the question-making process as we have seen last time. Now, how how does this work? If we take a look at what are our possible values, then we take a look at what are their probabilities. And we perform multiple steps. And in each of them, we just concatenate or put together in one set the two values with smallest probability. For example, if we have three possibilities as over there, we have probability 0.4, 0.3, 0.3. We just put together the two of them which have the probability 0.3. Those are the smallest ones. Now, that's the first step. Now, in the second step, we have just two nodes, 1 and 2 and 3, which were put together in the first one. Then we put them together again, creating one set, and then we go back, and as we have concatenated them, we assign them code words or symbols at the end of the code, either ones or zeros, and split them back apart. And in this way, if we first put together 2 and 3, then put them together with 1, and then go back, we assign 1 to 1 and 0 to 2 and 3, and then we go back even further to split 2 and 3, and we assign to this 0, which is the code of the set 2 and 3, 1 for 2 and 0 for 3, getting us the code word of 2 and 3 separately as 0, 1 and 0, 0. Now, generally, if we want to find the Huffman code of any random variable, just to summarize, so also doesn't work. Imagine the values of x as nodes of a tree. And then what we do is concatenate two values with smallest possible probability. Into single node. Then we just repeat this until we have only one node left. At this point, what we do is that we assign to this one node an empty string as its code word. To this full node with all elements. And then we go back through this procedure in a reverse, and for any concatenation going from back to the beginning, we put 1 and 0, we assign 1 and 0 as the continuation of the corresponding code word. And the continuation of the code word. And then we proceed until we are back at the original set. Until we have a code word for all original values. Now, this works for constructing a binary code. That's what we will be doing, most. Now, in some literature, you can read that for the pasting of ones and zeros, sometimes you paste, some literature mentions pasting 1 to the values with larger probabilities and 0 to the values with smaller probabilities. In some literature, it is reversed, but in the end, it does not matter, because we produce a code which just have zeros and ones switched, and for the code lengths, it doesn't make any difference. Now, this works for a binary. This works for a binary coding. If we have a non-binary, ternary, quaternary coding, so a d-ary coding, instead of concatenating 2 values, we concatenate 3, 4, basically d values. On the way forward, on the way back, we assign 0, 1 up to d minus 1. So for a ternary code, 0, 1, 2, and so on. And for us to be able to cover all of the options, we need a certain number of divisible elements. We need d plus k times d minus 1 elements. If we have less, for example, if we have 1 missing, we need to add auxiliary variables with 0 probabilities. We need to have d plus k times d minus 1 values if needed at values with 0 probability. Now, let's take a look how this works on an example. It might seem a bit cumbersome, first concatenating the values and then splitting them back, but it actually isn't that hard. Now, first we want to construct a binary Huffman code of a random variable which has 5 possible values with the corresponding probabilities given in the table. X is 1, 2, 3, 4, 5, and the probabilities are 0.25, 0.25, 0.2, 0.15, 0.15. Okay, so first we repeat the steps of concatenating values with the smallest probabilities. So let's take a look. 0.25, 25, 0.2, 0.15, 0.15. So these are the first candidates for concatenation. So we put them together. So what we do is establish a new random variable with 4 possible outcomes, and the last one is labeled as 4 or 5. Here 0.25, 0.25, 0.2, and then we have a sum of those probabilities producing 0.3. Now in the next step, we concatenate again 2 values with smallest probabilities. Now the smallest one is 3 with 0.2, and we need to concatenate it with 1 of those which have 0.25. At this point, it doesn't matter which one, we can just choose randomly or as we'd like. It's not important for the result. Well, it can be important for the final encoding, but not for the optimality of the code. It actually doesn't matter. So let's, for simplicity, take those 2, right? So 2 and 3. So we have x, the x, 1, 2, 3, 4, 5. Probability is 0.25 here, 0.45, and 0.3. Now in the next step, let's take a look. 0.25, 0.3. Those are the ones with smallest probabilities. So we put them together, get 1, 4, 5, and 2, 3 as nodes. Here we have 0.55 and 0.45, and then we just add them all together to produce a final set. 1, 2, 3, 4, 5 with a probability of 1. Okay, at each step we have just put together 2 values, and then we have added their probabilities. So this is the forward approach, then we need to take the backward approach, go from back to the beginning, and for each subset which we have concatenated, we continue the code word with either 1 or 0, depending on to which subset this did belong. So let's take a look. X 1, 2, 3, 4, 5 has the code word being empty. It's just a blank code word. Now we have concatenated these two sets, 1, 4, 5 and 2, 3. And now we pick one of them and add 1 as the continuation of the code word. Here the code word is an empty string, so we continue basically by starting the code word. So let's just start this with 1 and this with 0. Then we have put together 1 and 4, 5, so we are splitting this part. 1 and 4, 5. We copy the beginning of the code, and for this set which we have split, we write 1s and 0s as the continuation of the code word. So let's just take the one with the larger probability of having 1 as a continuation and the other one having 0 as a continuation. Okay, now what did we do? We put together 2 and 3, so we break them back apart. One, and we put 1 to one of them and 0 to the other of them. Let's keep in line with adding 1s to those with larger probability, but it doesn't matter, we can also switch them on. Okay, so here we have 4 values with 4 different code words, and then we have at the beginning put together 4 and 5. So we just copy the code words and put 1 to one of them and 0 to the other of them as the continuation. And this is our final code. It can be proven, that's not that simple to go through that, that using this algorithm, the code which is obtained is always optimal among instantaneous codes. The algorithm, by using this concatenating and then backward splitting, warrants always an instantaneous code, because the reverse procedure copies the questions approach. Remember from last time we were asking binary questions, yes, no, is it this or is it this? Okay, so here the first question, is it 1, 4, 5, yes or no? If it is this, then we ask, is it 1? Yes or no. Okay, and so on and so on. So such a code is always instantaneous, and such a code by using mathematical induction and playing with the expectations for a while, we obtain that it is optimal. We cannot find a code which would have smaller code lengths among the codes which would be instantaneous. Now here you see on the slides that there was a converse procedure taken, putting 0 to the others, to the ones with smaller probabilities, resulting in a code which is basically flipped, where zeros and ones are flipped. But it doesn't matter if somebody has the corresponding correct decoding table, he can decode our message. It doesn't matter whether ones and zeros are flipped. What matters is that the code lengths are exactly the same. Now, does it make sense? Now, what would happen if we'd like to construct not a binary, but a ternary code? So let's take the same distribution, let's take the same random variable, and let's encode it using a ternary code. So we need d plus d minus 1 times k values, which is like 3 plus 2 times k, and we have 5 values, so we do not need to add any artificial values to that. We can just proceed as before, but instead of putting together 2 values, we put together 3 values in each step. X, px, 1, 2, 3, 4, 5, 0.25, 0.25, 0.2, 0.15, 0.15. So we take those with smallest probabilities, which are 3, 4, 5. Zero 0.25, 0.25, 0.245. That's 0.5, right? And then we just add them all together. 1, 2, 3, 4, 5, x, px, into a set of having probability equal to 1. Good. So we just go into reverse. Here we add for the whole set of all possible outcomes, we add the empty string as its code word and proceed back as we did the splitting So 1, 2, 3, 4, 5. X, CX. And now we are constructing a ternary code. So we are assigning values 0, 1, and 2. So
It should be 3, 4, 5.
yes, it's 3, 4, 5 as one value. So we add 0, 1, 2, for example. Then we move to splitting back 3, 4, and 5, copying the beginnings of the code words, and at this point where we have split 3, 4, 5, we just add 0, 1, and 2 at their end. And this is our ternary encoding of X. And we know that it's the best one available. There cannot be another one with smaller expected code length. Does it make sense? You can take a look into the Covers and Thomas' book around to see the proof why the Huffman code is optimal. And the interesting thing is that this algorithm works locally as a greedy algorithm. Always it takes the two values with the smallest probability over and over and over, and at the end produces a global optimum. This is interesting on that. It works from the bottom and produces a global optimum by just doing local steps. But it is optimal at the end. Now, by assigning zeros and ones in a clever way, we can at some point think of the assignment of the code words either here or there as representations of the binary or ternary questions, as we have seen last time. If we are in a special situations, we even might imagine the splitting as just cutting the set of possible values in half, then again this in half, based on the probabilities. Now, the funny thing is that at some points, for some distributions, the Huffman algorithm does not need to yield unique coding, even not the same code words. If you would imagine a random variable with 4 possible values, with probabilities 1/3, 1/3, 1/6, 1/6, and you would run the Huffman algorithm, there are several, well, in the first step, you would concatenate this 1/6 and this 1/6 into 1/3. And in the next step, you have 1/3, 1/3, 1/3, and you can freely choose whether you concatenate these two and then move forward and produce a code having 4 code words of length 2, or whether you concatenate these two, concatenated to 1/3, with one of those 1/3, and leave the other for the last concatenation, and get different code words when one of them has the length 1, second of them the length 2, and the least probable 1/6s have the length 3. And you can do the math yourself, and you will see that those two codes are both optimal. They have the same expected code length, even if they look completely different. Okay, so it's when the probabilities are equal, it's up to you how you proceed, how you concatenate them. Okay? Now, in your homework, if you decide to do that, there are. I will just switch to the website. Homework assignments. Now, there is a zip file to download based on an algorithm produced. You will get 2 texts assigned. All of them are extracts from English books. And for the first homework, you are supposed to analyze the texts by looking into the individual frequencies of individual letters, and then finding, using the Huffman algorithm, finding the best possible binary encoding for the letters. Okay, so if you like, you can try this by yourself. You can either program the Huffman algorithm by yourself, or you can use some pre-programmed functions. You can do the homework in whichever software you'd like. You can use Python if you're familiar with Python. You can use the statistical R language, which I will be showing snippets later on, or you can proceed in Excel or in whatever you like. At the end, you're just required to produce a static PDF report of what you have done. Okay, so this is one of the homeworks, and covering the topic of entropy and coding. Yes.
So we only submit the PDF, not the source code.
In the PDF, there's supposed to be solutions, explanations, interpretation graphs, and key parts of your code. Okay, so you can paste the most important parts of your code which you used. It would help me to see if there is some problem at some point. It would help me to see where it was.
Okay.
Any questions to that?
When is the deadline for the first homework?
April 10th.
April the 10th.
Perfect.
So plenty of time. For the second one, it is always also April the 10th, and for 1 week before you go for the final exam, so that I have time to review it. But as I said, the homeworks are not mandatory. You don't have to do them. They're just for points. Yes, they are 4 points.
What is the second one?
The second one concerns statistical analysis. It will concern testing whether the frequencies of the letters in the two texts are the same, or whether they are not the same. Okay, we will finish talking about entropy today by seeing the entropy for continuous distributions, and then we will move to the statistical part, and we will see in the next week or the one after the methods needed to do that. Okay. Any questions before we move on? Good. You can try when looking in the tutorials. You can try finding the Huffman code for the exercise with the donkey here. You can try that yourself. If you get lost, you can just click here, and you will see the solution in the Marast system. It's explained there how it's done, but it is basically applying the same algorithm forward and backward. Okay, for two possible distributions of x, and so you can try doing this. Now, so far we have to talk we have talked about the entropy of discrete random variables. We have seen how it relates with the code lengths. We have seen that the entropy is the lower bound, the lower bound for the expected code lengths for any instantaneous code. Now, similarly, as for discrete random variables, we can define the entropy also for continuous random variables. Now, you remember that at any point where in discrete variables we were talking about probabilities and then we were adding them up, then analogously, when talking about continuous variables, we were working with densities and we were integrating them up. So in the same way as the entropy was defined as minus the sum of probability times the logarithm of the probability, in the continuous case, the entropy, or to separate them, it's called the differential entropy, is defined as minus the integral of density times the logarithm of the density. Definition, let X be a continuous random variable with density F. The differential entropy of X is defined as minus integral density times the logarithm of the density dx. If the integral exists. If it diverges, it is not defined. Now, the entropy of discrete random variables was defined as capital H of X, and it was the minus sum probability times the logarithm of the probability. Now this is an analogy, but it is not completely the same thing. That's why it is denoted with a small h. And we will see how it relates with the entropy of discrete random variables. Again, as with the discrete entropy, we are putting 0 logarithm 0 being equal to 0 to just follow in the line of the limit. And it is, again, the expectation of some informational value. In this case, the informational value is the minus logarithm of the density, which is again an analogy to the informational value for discrete random variables. The problem here is that the entropy is not the same when we transform the random variable in some way. For the discrete random variable, the definition used only the probabilities. So it doesn't matter whether the values of the underlying random variable were like 1, 2, 3 or 4, 5, 6. Only their probabilities mattered. Now in this case, because we are integrating over the real line, if we transform the random variable in some way, the entropy changes because the units of measure can actually change. So the differential entropy depends on the units of measure, which change when we scale the random variable by some factor. It can be shown that the differential entropy of a linearly transformed random variable can be found as the differential entropy of the original one plus the logarithm of the absolute value of the scaling factor. This might sound weird, but it can be proven quite simply by working out what is actually the density of a linearly transformed random variable. Now, the interesting thing is how the entropy behaves for a couple of distributions which we are already familiar with. Now, suppose we want to compute the differential entropy of the uniform distribution on a interval from 0 to a. So, example, compute the differential entropy for x having the uniform distribution on the interval from 0 to a. Now, let's take a look. You remember from the beginning of the semester when we were talking about continuous random variables, you think about the Romeo arriving on a secret place, uniformly distributed on some bounded interval. The uniform distribution has a density which is constant on this interval from 0 to a, and otherwise it is 0. And now from what we know about densities, we know that they need to integrate to 1. Now this is a rectangle. If this rectangle has a base of a, it needs to have the height of 1 over a, so that they together produce 1. Okay? So the density is equal to 1 over a. For x being between 0 and a, otherwise it's 0. So let's compute the differential entropy minus integral minus infinity to infinity fx times logarithm fx dx. Now, this is 0 for x's which are not in the interval from 0 to a. Yeah, because then we get like 0 logarithm 0, getting us a 0. So we just integrate between 0 and a. So minus integral from 0 to a, and now 1 over a, logarithm of 1 over a dx. And now this 1 over a logarithm 1 over a does not contain any x in it. So it is basically a constant. And if we integrate the constant, what do? We just multiply it with x, right? So we'll get that it is minus primitive function 1 over a logarithm of 1 over a from 0 to a, which is like, times x. 0 to a. So this is minus 1 over a logarithm 1 over a times a, minus the same with inserted 0, but that's 0. So this a and this a gets cancelled, and we'll get that this is minus logarithm of 1 over a, which is just the logarithm of a. Okay, so this is the differential entropy of the uniform distribution on 0a. Now, what is one of the major differences if you look at this result, logarithm of a, between the differential entropy and the discrete entropy? What was one of the key things that the discrete entropy always fulfilled? What were the possible values of the entropy for discrete case?
Okay.
Can you have a negative entropy for a discrete random variable?
No.
No, you can't.
So always greater than 0 or equal to 0?
Exactly. It is equal to 0 if the random variable in question is degenerate, meaning that it only has one possible value and the others are impossible. Otherwise, it is positive. If there is, it is the measure of surprise giving us, well, measure of chaos in the system. Now, in this case, logarithm of a, that's 0 for a being 1. It's positive for a being larger than 1, and it is negative for a being less than 1. Okay, so the differential entropy can be positive, it can be 0, it can be negative. That's one of the differences, and that's why it isn't a complete representation of the measure of surprise in the system. It is not. It is not directly analogous to the discrete entropy. Now, does it make sense? Let's take a look if we would, instead of if we were to move from the uniform distribution to the normal distribution, how would the entropy of the normal distribution look like? So again, an exercise. Point hx for x being normally distributed with parameters mu and sigma square. Now the density for a normal distribution is 1 over square root of 2 pi sigma square e to the power of minus x minus mu squared over 2 sigma squared for all real x's. Yeah, looking like the bell curve. The differential entropy is then the minus integral of the density times the logarithm of the density. Let's just rewrite this density times logarithm of the density. Let's keep this density here for a while. And see what the logarithm of what the density looks like. If we have a logarithm of a product, we can break it into sum of logarithms, right? We know that logarithm of like a times b is logarithm a plus logarithm b. So it is the logarithm of 1 over square root of 2 pi sigma squared plus the logarithm of e to the power of minus x minus mu squared over 2 sigma squared. Then we can imagine that this is basically 2 pi sigma squared to the power of minus 1/2. And if we have a logarithm of something to some power, we can put the power outside. So this is minus 1/2 logarithm of 2 pi sigma squared plus, and now depending on the units of measure of the entropy, this logarithm may be binary, it may be natural, it may be whatever we like, but this exponent can be put outside of the logarithm. So we'll have minus x minus mu squared over 2 sigma squared times logarithm of e. Yeah, if it's a natural logarithm, then this is equal to 1. Otherwise, it's different constant. So we now then insert this over there. So minus fx times, and now minus 1/2 logarithm 2 pi sigma squared minus, and now, yeah, I'll just break it down like this. Minus x minus mu squared over 2 sigma squared logarithm of e, like this, dx. Now we can break it down into two distinct parts, into two distinct integrals. In the first one, we would have fx times, well, something which does not depend on x in any way. So we can put it outside of the integral. These minuses would cancel, so we'll get that this is 1/2 logarithm 2 pi sigma squared times the integral minus infinity to infinity fx dx. And then we would have minus minus, so getting us plus. The logarithm of e is a constant, 2 sigma squared is a constant, and then we have the integral minus infinity to infinity x minus mu squared density dx. And now there are several things which we already know. We know what is the integral over a density of a random variable. Yeah? For any random variable, what happens if we integrate its density over the whole real line? What do we get? We get 1. So this is 1. Okay. Now in the second part, we have integral from minus infinity to infinity something times density dx. Now what is this? How can we rewrite it? Yeah, that's a function of x actually.
That's the. I don't want to say the wrong name, but something with.
Go ahead.
Variance? No, like,
At the end, this actually is a variance. Now, you can imagine that integral of minus infinity to infinity of x fx dx is just the expectation, right? The integral of, let's say, gx times fx dx is the expectation of g of x. Okay. So this thing is the expectation of x minus mu squared. So this is the expectation of x minus mu squared. And now mu for the normal distribution is the expectation. So it is the expectation x minus expectation x squared. And that's what's that? That's the variance. And variance is sigma squared. For the normal distribution, it's the second parameter. Okay. So here we have a sigma squared, which can get cancelled with this sigma squared, getting us 1/2 logarithm of 2 pi sigma squared plus 1/2 logarithm of e, altogether getting us 1/2 logarithm 2 pi sigma squared times e. Okay, so first of them, the differential entropy does not depend on mu. It does not depend on whether we shift the bell curve to the left or to the right. It does, so on the expectation, it does depend on the variance, sigma squared. If the variance is larger, then the entropy will be larger with a logarithmic progression. And we can see that if the variance is small enough, then the differential entropy again can be negative. Now, if the variance is smaller and smaller, the logarithm of that gets closer and closer to minus infinity. We will see at the end that the normal distribution has, among all distributions, the largest entropy. Now, you remember for distributions which were discrete, the entropy, the differential entropy, was always non-negative. And when was the entropy largest for a discrete distribution on some number of possible values? When was the entropy largest? Suppose I have a distribution on certain points, let's say on 4 possible values. When is the entropy on this largest?
They were the most diverse ones.
And what does this mean?
So one of them was very big, one of them was very small.
No, that's actually the other way around. Okay. In one of the probabilities is really big and the others are small, the entropy is smaller. If one of them is 1 and the others are 0, so there is no chaos at all, the entropy is 0. And as we have shown last week, using the Kolbe-Weiber divergence, is that the entropy is largest if the distribution is uniform. Okay, so for discrete variables, the discrete entropy is largest when the distribution is uniform. For continuous random variables, we'll see at the end that the normal distribution has the largest entropy. Now, let's take a look. What is the relation between the differential entropy and the discrete entropy? You can imagine that whichever distribution we have, if it's continuous, we can always slice it up into distinct parts to get a discrete distribution, right? For example, if we are observing the wave of people, we can either represent the wave as a continuous variable, which, for example, would have the normal distribution with some expectation, some variance. Yeah, like this. Or we can slice it up into distinct categories. One category, other category, other category, other category. Yeah, for example, by 10 centimeters. And then we would have a discrete distribution, and we would be talking about what's the probability that the weight of a person is between 50 and 60 kilos, 60 and 70 kilos, 70 and 80 kilos, and so on and so on. Okay? And we would assume that such a variable, when discretized, would have an entropy somehow related, somehow related to the entropy of the continuous random variable. It can be shown that they indeed are related, and for this we need to take into account a partition of the possible values, and we need to observe how it behaves. Now, well, this is nothing which would come up on the quizzes or the final exam. This is just something interesting which you can get back to if you ever need that. Now, if we slice the set of values which we are observing into discrete, distinct subintervals, and we construct a discretization of a random variable, and we want to compute its entropy, what we can work with are the probabilities of the individual intervals. Okay, we can take a value which is continuously distributed and just find the individual probabilities of the values. Suppose it has values which are the starting points or the end points or the middle points, doesn't matter for this case. And the probabilities are just this area put there as the individual probabilities of the discretized version. Now, we can then take the probabilities and think about them as, well, the integral of the density over the individual part over the individual, box. And that's the density, the difference between the distribution functions at this point and at this point. And then applying things what we know from the calculus, we can always find a point somewhere in the middle here, so that this area is the same as a rectangle, which, if I would draw it more in depth, now this area is the same as if we took that area for a distinct, this length of this is some delta, and This is sum of the values here. So this length times this length is the same. We can, by using the Lagrange theorem, find always such a point. And now when we do, for each of the partitions, we can just take a sum over those points, take the functional values of the densities, multiply them by the deltas, and get the same integral as we had. So the entropy of the discretized, the sliced up random variable, is just computed as any other discrete entropy. So minus some probability times the log of probability, and we'll go over the individual probabilities, which are the densities at the individual points times the length of the slices, and we insert them, probabilities, in the formula for the entropy, work with the logarithm for a while, and at the end we get that it is the sum of density times the logarithm of density times delta minus logarithm of delta times the sum of probabilities. And sum of probabilities is always equal to 1. So we get that it is just the logarithm of delta. So if we take a discretization of a random variable into slices which are exactly equal to delta, here delta individual slices, individual discretization, then the entropy of such sliced discretized random variable relates to the differential entropy, because the first part, for delta being small, converges to the actual differential entropy. Okay? And if we put the logarithm on the other side, we'll see that the entropy of the discretized random variable plus the logarithm of the length of the boxes converges to the differential entropy. So this is how it relates. If we take a continuous random variable, don't want to work with it as being continuous, split it into some brackets which have the length of delta, for example 10 centimeters, or 10 centimeters when talking about height, or 10 kilos when talking about weight, or whatever we like for a concrete case. We see how the entropy of the slice of the discretized variable and how the entropy of the continuous version of the variable are linked together. Okay? Does it make at least a bit of a sense? Yeah. Now, we can imagine the delta, the length of the individual slices, to be measured in a decimal scale, or if we are working in a binary representation, we can think about it measured on a binary scale. So we have like decimal places in the terms of a binary representation. So if the deltas are like 2 to the power of minus n, then this means that the entropy, the logarithm of this is then minus n. So the difference between the differential entropy and the entropy which arises from the discretization of the random variable is just n bits, which is the information lost by taking the variable and slicing it down into the individual pieces. Okay, so basically by taking a variable, slicing it down into some pieces, so basically rounding the information given by the continuous variable, then we just lose some information by that. Now, for the discrete entropy, we have seen if we have two variables, x and y, we have seen that we can establish the joint entropy, we can establish the conditional entropy, we can establish the mutual information. Now, we can do the same using the framework of continuous random vectors, also in the continuous case. So if we take a two-dimensional continuous random vector, for example, if we are measuring the height and weight of people, seeing how they relate, we can find the joint differential entropy by taking minus double integral of the joint density times the logarithm of the joint density dx dy. That is again an analogy to the minus double sum joint probability times the logarithm of the joint probabilities. We can, in the same way, define the conditional differential entropy by using the conditional density in the logarithm, and by seeing that the conditional density is the joint density over the density of the condition, as we have seen a couple of weeks ago how this works, how we can work with that, we can prove the chain rule as for the discrete variables, so that the conditional entropy of one random variable given the other is the joint entropy minus the differential entropy of the other one. So this is just a continuous analogy of what we already have. We can similarly define the relative entropy or Kullback-Leibler divergence as, well, the integral density times logarithm of density of one over density of the other, so the distance between two distributions measured in a similar way as for the continuous ones. And we can, in the same way as we did for discrete variables, define the mutual information between two random variables as the integral of joint density times the logarithm of joint density over the product of marginal densities. This is the same as we had for discrete variables, but instead of sums we have integrals, instead of probabilities we have densities. Now, if we take a look at this, then we can immediately say that if x and y are independent, what would happen regarding the mutual information? What does it mean that x and it would be equal to 0, because for continuous variables we know that they are independent if the joint density is equal to the product of marginals. So if the joint density is equal to the product of marginals, we are dividing two same things over there. We would have a logarithm of 1, which is always 0. Okay? So the same way as for discrete variables, the mutual information for continuous variables is some kind of measure of dependence. Yeah, like the distance between the actual distribution and its optimal version if it would be continuous. The same rules as for the joint entropy are in place. We can draw the same Venn diagrams as we did for the discrete entropy. Yeah, the joint entropy is, well, basically conditional entropy of one given the other plus conditional entropy of the other given the first plus the joint information, mutual information, and so on and so on. And the interesting thing to know is that using the fact that the relative entropy is non-negative and working for a while with the discretizations of the random variables, it can be proven that if we slice them up using a delta grid and working out the entropies of the sliced variables, we can find that the mutual information is for small enough delta equal to the mutual information of the continuous ones. Okay, so if we would be observing two random variables, for example, the height and weight of people, we would slice it up into different, well, categories, and we would compute the mutual information of x and y based on just the probabilities of the individual categories. We would get, if the categories are, well, small enough, we would get something which is really close to the mutual information of the categories of the two variables if we would be working with them as continuous. Okay? So if we want to use the mutual information for investigating a relation between two variables, it doesn't matter whether we use them in a continuous way, which is often harder, or whether we slice them up into distinct categories, into some subcategories, for example, by centimeters and kilos for the height and weight of people. Okay. Now, proving this is just a tedious work with sums and integrals, and whenever you encounter, well, the concept of entropy, you can refer to this lecture. To this lecture, you can read how it relates. Now, the last thing is to prove that for any continuous random variable with a fixed variance, it can be proven that its entropy is always smaller than or equal to the entropy of a normal distribution, basically meaning that the normal distribution has the largest entropy among all continuous distributions with a given fixed variance. Now, proving this is actually simple, going from the old fact that the relative entropy is non-negative and measuring a relative entropy between one random variable with a given fixed variance and a general density of f, or density f, comparing it to the Gaussian distribution. Okay, so the relative entropy between any distribution continuous with density f and Gaussian distribution with density, let's say, phi. That's the integral fx times logarithm of fx over phi x dx. And the logarithm of a division is logarithm of this minus logarithm of this. So we'll get that this is integral minus infinity to infinity fx times logarithm of fx dx minus integral minus infinity to infinity fx times logarithm of phi x dx, where phi is the density of normal distribution mu sigma squared. And going by the same as we did before when computing the entropy of the normal distribution, we would see that if we break down this logarithm, we break down this integral into two parts, then this first integral is equal to 1 for any density of f. If this is a general density, then the integral of it is always equal to 1. So, and in the next part, we would get the same integral here, and we are assuming that the two distributions have equal variance, sigma square. So this, regardless of which density we insert here, we know that this is the entropy of an normal distribution mu sigma square as we computed before. And here we have integral fx logarithm of fx dx, which is minus the entropy of distribution with density f. And now we know that the entropy of the normal distribution minus the entropy of any other distribution is basically their relative entropy, the Kolb-Leibel divergence. And we know, we can prove from the Jensen's inequality for continuous distributions, that it is non-negative. This means that the entropy of the normal distribution is largest among all distributions with equal variance, and it is equal whenever the distribution is small. Okay? So we know that the normal Gaussian distribution has maximal entropy among distributions with, well, among continuous distributions. Okay? Good. So this will be, this is just fragments of results which have been connected with the differential entropy regarding, well, continuous random variables. But this is nothing which would come up on the final exam or the quizzes, just the bonus material for you to refer to whenever you'd encounter it in practice. Okay, the important thing to get from this part is how to work with the entropy of discrete random variables, with the joint entropy, relative entropy, mutual information, conditional entropies, and so on, and how it relates with the coding. Okay? Good. Yeah, so we'll make a break now and continue that.
is there? X86. X86. I'm trying to send an interruption flag to print from terminal, but it breaks here.